So this time this is Thevenin number 2. Let's start with the circuit. Thevenin number 2. So we have a pretty long circuit here. 400 volt supply with quite a few resistors. Let me see this. Let me clean this a little bit already. So, oh, wait a minute. This looks a little dirty. Okay, so this is the voltage source, plus and minus. Here we have wire, resistor, resistor, another resistor, current source for a change in an amount of 0.75 amp. And we have another resistor here, another resistor here, another resistor here, and open terminal A and B. Let's go ahead and fill in the amount. This is 100 ohm on the top. Okay. This also is 100 ohm. And here on the top we have 150 ohm. Well, we already talked about the current source in an amount of 0.75 amp. This fellow here is 200 ohm. And the one on the top is 300 ohm. And this one on the right is 100 ohm. So what we have to do is transform this given circuit to an equivalent Thevenin circuit of voltage V Thevenin, which we have to determine, accompanied by a series resistance R Thevenin, which we have to find out, and B. In other words, the given circuit will supply energy just as much as this equivalent Thevenin circuit would to a given load, to the same load. And we will hook up the load to the terminal AB eventually in such a manner that the load will match the Thevenin resistance, in which case we will have the power being Pmax, max power transfer. So in this problem, we have to determine the Thevenin voltage, Thevenin resistance, and how about the max power that can be delivered from this circuit. Okay, so this is the idea. So it looks like we could use source transformation technique to do the job. Using source transformation technique, we have the 400 volt source with 100 ohm transformed to a Norton equivalent circuit given by 400 over 100, that's a 4 amp current source, which is the Norton current after Professor Norton. Let me clean this just a little bit. Let me redraw this. So this is 4 amp, wait a minute, okay, current source, which is the Norton current with parallel resistance in an amount of 100 ohm. So we will replace the given 400 volt with the series 100 ohm by 4 amp with a parallel 100 ohm resistor in the given circuit. So that's the game plan. So our new circuit would look like let's be careful here. A lot of things. 4 amp, okay, and we have what now? 100 ohm resistor. Then we had previously 100 ohm already. Now we will have the remaining part just the way they were, 150 ohm here on the top, and we have 0.75 amp current source. Then we have the 200 ohm resistor, and then we have 300 ohm on the top, and then we have 100 ohm on this side, ohm, and the one on the top is A and B. So this is our new circuit. So all we have done here is we transformed the Thevenin 400 volt 100 ohm circuit to a Norton 4 amp 100 ohm in a parallel circuit. So at this point we notice that the 200 ohms are in parallel. So 100 ohm and another 100 ohm in parallel gives 50 ohm. 100 times 100 divided by 100 plus 100. So that is 50 ohm. So we have 4 amp current source with 50 ohm resistor. So what else? The remaining part are to be copied carefully, such as this 150 ohm on the top. The current source is 0.75. Let's remember that. We will copy this just the way it was. The remaining pieces will have to come sit here, such as 200 ohm, 300 ohm on the top, 100 ohm on this side, and onto the right A and B open terminals. So what we have done here is we have simplified the 200 ohm resistors to give a total of 100 parallel 100, that's a 50 ohm equivalent resistance. Now at this point we will check the Norton source back to Thevenin, meaning we have the 4 amp in parallel with 50 ohm resistor being same as 4 times 50, that would be 200 volt voltage source with the 50 ohm on the top. So this is the source transformation. So if we do this way, our circuit becomes 200 volt, then we have the voltage source with the 50 ohm on the top. What else? We have to copy the remaining, such as the 150 ohm. Wait a minute, this is 150. Okay, 150 ohm. Then we have the current source. Need to be careful here, 0.75 amp. And then we have the remaining things, such as 200 ohm here with a 300 ohm on the top, and 100 ohm here on this side with the A and B on the far right. So that will be 50 and 100, 150 on the top is 200 in total. So we have plus minus 200. Wait a minute. 200 volt, and on the top we have 150 plus 50, that's a 250, and then 200, I should say. Wait a minute, 200 ohm, and then remember the current source, 0.75 amp. This is getting tricky to write it. So we have the 200 ohm here And then we have the 300 ohm on the top. These lines are continuous, of course. Remember to join them properly. Okay, then 100 ohm on this side. Need to be careful. And here's A, here's B. And so far so good. Need to be careful here. So our game plan will be just the same way. 200 volt voltage source with the 200 ohm on the top is the Thevenin source. We will change that to Norton. The way we do that is divide the 200 volt by 200 ohm, giving us 1 amp current source. Then we will pull the 200 ohm resistor in parallel, so that would be the equivalent Norton source. So that would be, as I said, 1 amp current source, right, with the 200 ohm, which we have to pull and keep it in parallel. And then what else? There comes the current source now. We're simply copying this parallel all the time. That's how we will do for now. We will see what we could do a little bit later about this source. Now remember the 200 ohm here on the right. Need to copy it. 300 ohms sits on the top as we have it, and 100 ohm just about done here. This is A and that's a B, but let's write the 100 ohm here before we forget. So what do we have now? Well, looks like we have 1 amp going up, 0.75 coming down. So that leaves us a balance of 0.25 amp going up. So that's the important part here to realize. Again, let me explain it. We have 1 amp current going up. They have a common node, and 0.75 is coming down. So in effect of 0.25 amp going up, then we have two resistors here, 200 ohm and the 200 ohm in parallel. Notice that. All we have done is we have combined the 1 amp going up, 0.75 coming down to give a balance of 0.25 amp current source going up. Then we are copying the two resistors just the way they were in the circuit. What else? Then the remaining things have to be copied, such as 300 ohm here needs to be copied. 100 ohm comes back here. Supposed to come back here, so it's A and a B. So at this point, we notice 200 ohm and 200 ohm are in parallel, so that will give us 100 ohm. When we combine 200 times 200 divided by 200 plus 200 gives us a total of 100 ohm. So in effect, we have 0.25 amp current source accompanied by 100 ohm resistor in parallel, which is from the parallel combination of 200 ohms to 200 ohms. So on the top we have 300 ohm as it is. Then next we have 100 ohm on the right. So A and B and B. All right. So now what? We have the 0.25 amp accompanied by 100 ohm, which is a Norton. Now we have to take it to Thevenin, which we can do when we multiply the 0.25 and the 100 ohm, which gives us a voltage source of 25 volt. That's nice. Then we have this fellow 100 ohm go to the top. All right. Let me clean this just a little bit here. Sometimes it's easy to mess a little bit in these numberings. This is 100, folks. Alrighty. So now, coming back to this circuit, we have the 300 ohm here, which will stay as it is here, and then the 100 ohm on the right, and we have A and B. So far so good, I suppose. So that gives us a total of 25 with the 400 on the top. Okay, so what we have then is we have 25-volt source with 1 and 300 making 400 in total, and then we have 100 ohm on the right side. There's A and there's a B. So now what? Now we will again transform the 25-volt and 400 Thevenin configuration to Norton. So we will have a current source in an amount of 25 divided by 400. Now how much would that be? 25 divided by 400 is primarily 1 over 16. Is that right? I think so. Alrighty, so that will be the amount of this current source. Let's leave it in fraction. We will have to be multiplying this later by some big numbers, so it will be fine. 400 comes down here to sit in parallel. That's what happens with the Norton, as we all know, signal. Then this 100 ohm, and then here's A, and here's a B. So this time we are trying to combine 400 parallel 100. What do we know? We multiply 400 times 100 divided by 400 plus 100, that's a 500. So that will be 80. Is that right? Yep. So we have the current source 1 over 16 amp accompanied by 80 ohm resistor, and there is A and a B. So this is actually the Norton equivalent circuit. Now we can change this to Thevenin when we multiply 1 over 16 by 80. So we end up getting 116 times 80. 1 over 16 times 80 is 5, right? So we have 5 volt here. This is our Thevenin voltage. 80 ohm here, which is our Thevenin resistance. Here is A and this is B. So P Thevenin is 5 volt. That's our answer. R Thevenin is 80 ohm. Good looking numbers. Now when we hook up the load, which is RL, to make P become P max, RL needs to be the same as R Thevenin, also 80 ohm. And then P max is given by PTH squared over 4 times RTH. So when you plug the numbers, PTH is 5 squared 25 divided by 4 times RTH is 80. So that will be in watt. So P max is, we can cancel, so 5 over 64 watt. Wait a minute here, what happened? P max is 5 over 64 watt. Okay, that's what it is. Alrighty, so that's the answer for the max power transfer. Hope you enjoyed it. I have a good time. Take care.